Thanks for joining us. This is the session on teaching applied DP. The format that we're going to use is we're going to have two demos from two different courses taught at two different institutions that have experimented with teaching applied DP. And then we're going to have a little panel discussion. The goal here is to sort of share ideas and surface ideas and hear what folks have been doing in this space. And we'll pick it up with the demo by Moshe. Go ahead.
Hi, thank you. So thank you everyone for joining, despite the intense competition. This demo, as its name hints, is going to be a show, don't tell kind of thing. So instead of telling you what applied DP course looked by us, we're going to try to let you experience it. My name is Moshe. This is a joint work with Katrina and Tomer, not in the sense of work as a paper, but as a course, and you'll see in a moment what does it mean. So I'll start to dive right in. This is a graph, and we'll try to figure out what's going on here in a moment. Generally speaking, it's going to be some privacy measure on the y-axis, some accuracy loss on the x-axis. It has to do with logistic regression, and there's like two methods we're comparing here, just so you have a general idea of what I'm trying to explain. And here's the setting. So we took dimension d equal 100 and 100 points, and we tried to solve a logistic regression problem with 5 steps of gradient descent. That's the general problem. We wanted to do it privately, so we chose epsilon in the range, like we ranged epsilons from 1 to 7, give or take. Delta is 1,000th, and we need to maintain privacy somehow. So we're here focusing only on what's effectively labeled differential privacy. So one option was just to do randomized response. You get your labels, you flip them with some probability, and then you continue the pipeline vanilla, no changes. And the other option is noisy gradient descent. We didn't even bother with the stochastic part, so every step is using all of the points. And noisy gradient descent, we got the great intro from Ilya, so you know how it works. So the accuracy is just like measuring the accuracy of the results and the test data. And the privacy we measure empirically by running a reconstruction attack. We use linear regression just because it's faster. We know that officially you have to do linear programming, but it gets basically the same results. Okay, so this is the setting. If you don't understand like some of the details, you're not familiar with one of the techniques, it doesn't matter. This is a high level kind of idea. So now let's look again at the graph now that we know what's going on. So x-axis is test loss. Y-axis is the reconstruction error. The higher the reconstruction error, the better the privacy is. So it makes sense that bigger loss, bigger privacy. The orange line is the noisy gradient descent, and the blue line is randomized response, both using the same range of epsilons, which is not necessarily the type of graph we would expect to see. So instead of explaining what's going on, let's take 3 minutes, because I didn't prepare enough content for the whole 15 minutes, and just discuss with your neighbor, what do you think is going on here? I'm serious. Let's take a few minutes and do it with your neighbor, not with me. Oh.
The reconstruction attack is carried out using just the coefficients that are.
Yes. Oh, yeah. I took from all the gradients. I took the gradients from all 5 steps, and I treat it as linear queries effectively, and I run reconstruction attack. Okay. Great. Discuss with your neighbor.
Reconstruction error is like so yeah. There's like many data.
Yeah, each one is like from epsilon ranging from 1 to 7.
Yeah, so.
But it looks like the reconstruction error.
They both range the same range of epsilons. Range of epsilons. X-axis? Test loss. Test loss. No. Cross entropy. Cross entropy. The loss that we were optimizing for.
I got it. There's 100. Again, we're
Summation is 100. Number of points is 100. It's exactly the minimum that's required to solve it uniquely.
So it's the right way. Okay.
Okay. So, hey everyone. I'm sorry, I'll have to stop you. Partially because I don't want you to get the solution before I reveal it, and partially because still I don't have that much time. We'll get back to it. But for now, this was supposed to be about teaching DP, and instead it's about like some weird experiment. So like, why am I here and what am I trying to do? So there's a course taught by Katrina at the Hebrew University for like, I don't know, 6-7 years already, called Foundations of Differential Privacy, which is the classical theory course we all know and love. Teaching all of the properties and techniques that are the basis of modern, modern, all of it is modern, differential privacy. Since last year, this academic year that just ended, there's another course that Tomer Shoham and we're both Katrina's PhD students, taught concurrently with try to show how. I'll just try to show through this example, how does this course work? So I had the word logistic regression. So students were not required to take some introduction to machine learning or something like that before, but that was recommended. Still, we had to cover, so we covered the basic theory, pseudocode, and provided the code in class. And when I say implementation in class, that meant that as part of the lecture, if you see my videos, you see me programming in class, obviously using Copilot and things like that to make it quicker, but still, we programmed in class and had the people pointing out, no, you gotta, you forgot a parenthesis there or something like that, which is a great way to get people involved. There's the gradient descent, DP gradient descent part and the randomized response. So both of them we showed pseudocode in class and discussed it, etc., after the theory was taught in the theory class. And then implementation was done by the students after class. Now, the way it worked is we had 2 hours of lecture and then 2 more hours that we stayed in class after the lecture. The students were welcome to stay and work on the home assignment, talk to us about questions, whatever. Nearly every student, nearly every week stayed, even though it was not mandatory. Like they left either when we left or some of them stayed afterwards, which was, we did not expect that. But it became sort of a collaborative kind of dynamic. Then there's the reconstruction attack. The reconstruction attack were also implemented by the students, both linear regression and linear programming, at a different chapter of the course. So the course had like a few components. One component was attack, one component is privacy protection, and then this is like almost from the last weeks where we try to combine everything together in machine learning. And the evaluation was a significant component. So this particular graph, the students, the ones who didn't have a mistake in their implementation, got this graph at some point in their home assignment and needed to figure out what's going on. And that was part of their test to make sense of it and obviously, try to figure out if they didn't make a mistake, which led them to this, etc. Why? Why did we do it this way? So we had a few guiding principles. The first one was, which also gave the name to this session, it's like learning by doing. What we're trying to achieve is to better understand the theory by implementing. Students coded, I coded, but it was not an object-oriented programming or intro course. It was a course about differential privacy where the implementation helped us better understand things. This is an example from a lecture where we went through the ROC or hypothesis testing interpretation of differential privacy, where we're actually just doing ROC curves in class, etc., and through that trying to understand what's going on. In a way, people who did some empirical science, physics, biology, chemistry, and had the experience of sitting in a lab, got something that like math students usually wouldn't get, which is like you do something and you see something with your eyes and you try to figure out why it happened. And it's like nature gave it to us. It's not I wrote an equation or something. And computer science sort of can have it too by programming, and yet we don't use it as much. And this is, in a way, something we try to do. Particularly in differential privacy, it's a natural thing. So we actually ran experiments in class and at home and try to figure out what's going on. We used it to sort of encourage the student to become more of like a researcher and not only like, well, you need to differentiate this function, or you need to prove this tiny lemma. It's like, so here's an example that got me really excited. We had a bonus. It was 2 points out of 1 of 3 assignments. It was negligible. And this is just a few screenshots from one of the couples of students that assigned, and like they had a whole chapter about the P mystery. They were trying to understand why the bonus is like something doesn't make sense. It's the same kind of question, like why it is, and they tried to create all sorts of new graphs they came up with. And like the last sentence is the important one. This is a super interesting phenomena, but I'm afraid that after 3 pages of discussion, it is a good time to stop. And it was actually after 3 pages of discussion. Yes, one of those students afterwards became Katrina's student because he was very, I mean, he is a very strong student, but still, like not all of them were that impressive, but everyone was really involved. And finally, we had an interactive class. So 2 points about it. First of all, this is, I'm a little bit of cheating. Like we had video, like seeing the screen only during the break that people were talking, but actually people talked throughout the class. We just don't have any picture of it. And second of all, like we're really excited that we have this class to show. And from what I understand, Sharon like chose this class on purpose. Katrina was like constantly complaining about the fact that she got tired of being in classes where the chairs are bolted to the floor. And yeah, okay. And in Hebrew University, it was very hard, from what I understand, to convince the administration that it's not necessary. And students had exactly a class that looked actually very similar. And this was the interaction. And people sometimes just got up and showed something on the board, etc. Okay, so I have moments. So just let's figure out what the hell. I mean, what I think happens here, because it's just a hypothesis. So first of all, I'm adding 2 numbers just to make it clear. So the bottom one is the high epsilon and the top one is the low epsilon, which makes sense with both of them, right? Because low epsilon is higher privacy and more error, everything makes sense. But just like they don't belong with each other, but they do seem to sit like sort of on the same line. So the first thing you'll do is just extend the range of values. So indeed, epsilon equal 20 for the noisy gradient descent gets already close, and epsilon equal 0.1 for the randomized response. So it seems like things are sort of aligned, but still don't make sense. But remember that when I write epsilon, I don't know that it's epsilon. I chose epsilon, and based on that, I computed my parameters, and that's the amount of noise I added. Now, that epsilon is the upper bound. So in a sense, when you see a point here and I tell you this is epsilon equal 3 point something, that's a lie. It's an upper bound on epsilon, but actually its epsilon can be anything lower. So maybe, and I'm honestly meaning that it's maybe, this indicates that the analysis for noisy gradient descent in this particular setting is extremely, extremely conservative. And in fact, because we do have other experiments that show that the experiment for randomized response is like relatively close. So maybe what's happening here is that indeed just we have a very loose bound, and this is sort of a way to indicate how loose that bound is. That's it. So we got a tiny taste of what that course was like. And I would be more than happy to hear questions, recommendations, any proposal for collaborations, anything like that, after we're going to stay here after the panel. Thank you very much.
Another example. So one run, we'll give our next step out.
Okay, so I'm Zhen. Today I'll be introduce our course.
No, I was wondering if you needed a microphone, but.
Oh, right. No, yes, you do need. Yeah. No, I forgot. My bad.
All right, so this is much better. So hello everyone, I'm Zhen. Today I'll be introduce our course, CS208, Apply Privacy for Data Science. So this was taught in spring 2022, and I was one of the instructors together with Salil and James. And our teaching staffs are Daniel, Jayshree, Mike, and Connor. So this is our GitHub page. We actually have all the materials you can find online through this link. So I want to first introduce the audience, so our students of this course. So basically, the majority of our students are data science master students. So this is a very applied course. And plus, we do also have some students from other schools, including business school and Kennedy school and so on. So that's why we have a very different set of purpose compared to a pure theory course that was maybe designed for pure theory students. So I'll show you how we design the course. So this is our syllabus. So we start with the overview of the privacy attacks. So which basically want to showcase you can find the re-identification attacks, reconstruction attacks, membership inference attacks in like a lot of data science applications. And then we will provide a firm foundation of differential privacy. This includes the definition, interpretation, and also the basic property like composition, so on. And we will survey some like known basic algorithms. But important thing is when we teach this part, we also have this pair learning. So basically, when we have one lecture of theory together with a module, then it's more implementation oriented. So this implementation-oriented lecture is like after each theory course, which will let the students do more hands-on coding and implementation of the mechanisms. So we also include a review of the deployed systems in the real world. You can see here we survey the statistical releases by the U.S. Census, Opportunity Insights, and others. And other examples, including the machine learning deployments by Google and Facebook. And beyond this real deployment, we also include, we also want to show the non-technical side of privacy, which is important for like what you need to consider when deploy DP in practice. So like this includes ethical considerations, privacy law and policies, and also like other power dynamics in social technique systems. So this is our main site when design this course. As I mentioned, we emphasize real use cases. So before each lecture, we distribute this very curated reading material for the students. So this can include some like news articles and also the papers. This can directly relate to the actual deployments in the industry. So I think providing this contextual information is important because this can help the students can directly tie the theory learning in the lecture to the real deployment. So I think this is a very nice way of learning. As I also mentioned, we have this pair learning. So we we do have this implementation-oriented class. For example, this machine learning with DP, we provide the Python notebook here. Yeah. So this lecture can guide the students through this step-by-step process of turning theory into practice. In the rest of this demo, I'll showcase a homework assignment. So when we design the homework assignment, beyond the theory, beyond the basic understanding of DP theory, we do also try to have a homework assignment. Then this is a simplified version of some real-world deployments. So we want to showcase you can actually solve the real-world challenge by applying the basic technique you learned from the class. So I'll give you a demo for how we think about to design homework assignments. So this was inspired by the top-down algorithm in the 2020 census. So the top-down algorithm first adds noise to the histogram and then converts this convert the noisy histogram counts to macro data that match this noisy histogram counts. And then basically this approach can be viewed as generating DP synthetic data. So this DP synthetic data and then be exported to the census tabulation system to generate their data products. So basically this is the background. So for the course, we want the student to do a simple assignment on how to generate DP synthetic data. This doesn't have to be a fancy synthetic data generation algorithms like the minimum spanning tree algorithms. So we can just simply construct noisy histograms and then generate synthetic data that match this noisy histogram counts. So this is actually the basic concept of how we generate synthetic data, like for I guess for all kinds of synthetic data generation algorithms. Another application is this opportunity atlas. So this is a real-world deployment that use technique inspired by differential privacy to map the economic opportunities across the US while protecting personal data. So their method is based on regression model. So in the course, students might tackle a simplified version of this and then runs a very simple DP regression model. So this is how we think about to design this assignment. So this is our assignment. So basically, we asked the student to write a DP synthetic data function. As you can see, we provide the detailed guidance of how to generate this synthetic data. So the first step is you have to generate your data set, and then within this boundary, and then you can bin the data point using some grids. And then you construct a DP histogram of this data set and then post-process this histogram to construct the synthetic data. So we provide the detailed guidance on this. And the next step, we ask them to perform and evaluate the linear regression on the synthetic data. And we also compare this. We ask them to plot the bias and standard deviation. And we also ask them to compare this with the result of directly using DP regression on the data itself, on the real data itself. So the next, I'll show you a demo on how we tackle this. Give me 1 second. Let me open the notebook. Okay, so this is our notebook. The install OpenDP library is already done because it takes some time. So basically, we provide the helper function to generate synthetic data, and this function is to generate synthetic. Sorry, not synthetic data. The random data as a real data. And we also provide the helper function to plot the histograms. So as a background, although most of our students are data science master students, some of our students may have like different backgrounds. So we provide this function So for them to directly use this without worry about how to make these plots. Yeah, so this module basically have all the helper functions. And this part is how we use the OpenDP library to make the noisy histograms. So this function basically apply the noise to your histogram counts and return your noisy histograms. And then this function, the sample synthetic, basically takes the histogram, noisy histogram as the input, and then generates synthetic data that match this histogram counts. And this makes synthetic data basically is a chain that chains those these two functions together. Then you can input like put your bounds and the number of bins and automatically generate the synthetic data. So this is just a chain of these two functions. And then I'm gonna skip this part because this module is for the regression part. It takes a long time. So I'm not going to run this part of code, but this function is for the implementation of the regression model. So I'm gonna show you, so this is a short demo of we generated the data size of 1000, and within this bound, where x is only from -0.5 to 0.5, and the y-axis is from -1 to 1, and the histogram bin is said to be 20 within, like, we divide this whole domain into 20 bins. Yeah, so let's run this. And you can see we have the heat map for the true data, and this is heat map for the synthetic data. And you can see this is really close, although there's some like really minor counts in the other places. Okay, so although I'm not going to run the regression part, I'll show you the results on that. This is preloaded. So this is bias of against the number of records in the data, and this is standard deviation against the number of records in the data. And in the two plots, the orange line corresponding to the result of directly using DP regression on the data, and the blue line corresponding to you generate the DP synthetic data first, and then run a non-private version of regression model on the synthetic data. So as you can see for the bias, if we directly use DP regression model, our bias is actually converged to 0. Not converged to 0, but like very close. But with synthetic data, the gap is pretty clear. So basically, it's also match our intuition. Like using synthetic data will give us worse utility, but actually it also have some nice benefits. Like the engineer don't have to worry about changing their analysis pipeline because you can use synthetic data itself. And also it has nice post-processing property. You can actually enable to do more analysis. And for the standard deviation, because it's only for standard deviation, the difference is not that much. So I think like from this homework assignment, students can really get to see what is the benefit of using DP synthetic data versus using regression model itself. Okay. Yeah, I think this is also a good example of like some simplified example of what James also mentioned in the previous panel discussion. Yeah. Okay, I'm gonna conclude with some key takeaways from our course. It's slow. Wait. Yeah, some key takeaways from teaching this applied course is we want to share some real world scenario hands-on experience to make the learning processing more engaging and practical. And when we design the course, some mindset could be like we have to cover a lot of techniques as much as possible. But the lesson we learn is actually we don't have to. We just have to focus on the core principle over the techniques, because what we really want the student to learn is what to consider when they deploy DP in practice. So this could even involve some policy and also like infrastructure and data access and so on. So all these basic concepts. And the last point is we also hope by using the simplified version of real deployment, we hope the students can grasp the core concepts and methods used in these high-profile deployments without being overwhelmed by the complexity of the full-scale projects. And a lesson we learned is also like some simple solution often lead to successful DP deployments. So that's it. Hope you, yeah. Yeah, as I mentioned, we do have the GitHub page and it has all the course materials. Yeah.
Wonderful, thank you. Thank you for both of our demos. And now we're going to transition to our panel discussion.
Oh, yeah.
I guess we'll probably turn this off if anybody doesn't. Oh. I don't want to disconnect us from the remote participant clip, so I hesitate to do
You
that.
need this?
Yes, we do need mics of some sort. Maybe we'll give Rachel that one and then we can put this together. Don't worry about it. I mean, it's a little awkward, but.
I know.
Okay, good. Better than we know. It's hang on, this could be for you.
Okay. So I am like extremely honored to be here with our three distinguished panelists. Let's start by just sort of like briefly introducing yourself and a little bit about your sort of experience teaching applied DP, and in particular, what is the sort of audience of your courses?
Sure, thanks. Is this microphone working? Fantastic. So I'm Katrina Liggett. I'm faculty at the Hebrew University. As Moshe mentioned, for many years, I taught a DP theory course. And for a good number of those years, I felt like, man, it would be really great if we could have an implementation component to it. So finally, this past year, we played with it. And I'd love to reflect as we go on a little bit on some of the things that surprised me and that I learned from that. But for now, I think Moshe gave a good introduction to the course, so I'll pass it along.
My name is Joe Neer. I am a faculty member at the University of Vermont. And I got there in 2018. It's a fairly small university, and kind of from the beginning, I knew I was going to have to be able to teach an audience mostly of undergrads and mostly of people who didn't have a strong theory background, but were going to be software engineers. And so I felt like I kind of didn't have a choice. And so I've been kind of teaching. I wanted to teach a course in differential privacy, and I felt like it had to be applied. And so I, kind of did my best to develop one from the beginning.
Hi, everyone. So I guess I've introduced myself already today, but for those of you who didn't know me pre-OpenDP, I am a theoretical computer scientist by training, and most of my work and my teaching early in the days when I was working on differential privacy, probably for the first 8 years or so, were very much on the theory side, like really focusing on the complexity issues. For those who've seen my complexity of differential privacy survey, and what got us to introduce the course that Wenrong talked about was in part my interest and James' interest as we were getting more interested in the practice of differential privacy, involved in multidisciplinary research and the Privacy Tools project on that. But it came at the time we were making the pitch for OpenDP, and realizing that there was need for this. And as we were doing that, part of the case that we were making about why differential privacy adoption had been slow at that point was that there weren't enough people trained to do this outside a few organizations that could build up teams in this area. So that was one motivation. And the second motivation was more self-interested. I didn't feel ready to run an open source software project on differential privacy. And I thought, well, teaching a course on applied differential privacy was a way to fill that gap somewhat and build up my understanding of the challenges people were facing and how implementations work, so that we were more informed going into it. And very thankful that, yeah, James Honecker joined me in co-teaching and designing the first offering of the course. And then Wenrong talked about the great team we had for the second offering. The audience, Wenrong mentioned, at the same time Harvard was starting its data science master's program. So that seemed like a perfect fit. But here, courses are generally open to everyone. So we have a mix of those master's students, undergrads, PhD students. And so it's not a totally homogenous group.
I guess I didn't say audience very, very clearly. So we had a mix of undergraduates and master's students from computer science.
And in fact, that's an excellent, like, a transition into my next question, which is that you all spoke about the need for an applied DP course. What are the type of students you think can really benefit from an applied DP course as opposed to our sort of like existing theory courses?
So since I'm holding the mic, I guess I get to go again. So for me, it was clear from the start that adding an applied component to the theory course was going to help people understand the theory better. I thought this was going to make the theory course easier, more approachable, more understandable. And it was also clear to me that this would be helpful for people who are going to go on at some point, maybe to use differential privacy in practice. What I didn't anticipate is that it trained DP researchers really, really well. I had no idea that this was going to be one of the outcomes, but actually now I want all of my future graduate students to do the applied course, because somehow this mode of exploration that emerged in the context of the applied course was really, really inviting to students asking why and how and what if in a way that just didn't come out as much in a theory course. So that was a surprise for me.
So the same thing, right? Exactly the same surprise happened for me, and it helped me also, right? Like developing materials has helped me really get an intuition for the things, because like you try it, right, and see what happens. So I thought of my target audience originally as I kind of looked around at what were people doing in deployments, and it, like 100% of the time it was like somebody did their PhD in differential privacy and they went and led a team that implemented the thing. And I'm like, I'm not going to be like the person who has the PhD. They have plenty of, like, they're getting their education, right? But they have to have a team who's going to actually implement the stuff. And so I thought of my target audience as kind of two kinds of software engineers. One is the people below that person in the team who are actually writing the software that's going to implement stuff. And, they probably will never completely understand the theory, or there's a good chance of that. But they should at least understand some intuition behind what they're going for in these differential privacy mechanisms, and especially how to know what to look for in terms of warning signs that something is messed up. Like, what are the pitfalls to watch out for? The other target audience I had in mind was people who are going to go work at companies not in privacy. If those companies ended up doing something really bad for privacy, they should at least know the signs and be able to recognize that and say, I'm not sure this is okay. We need to go find some help. And so, my goal was really never to teach the theory. It was to teach people who probably weren't ever going to have the theory. But exactly the same thing happened, that I feel like it gives people this kind of grounding that enables them to understand the theory better afterwards.
So Katrina and Joe already said most of what I would say on this question. So I agree completely. As I mentioned earlier, the target audience was very much kind of, I think, like what Joe was talking about people who are going to be engineers or data scientists in industry or government, either working on a privacy team or working in some other area, and wanting them to be able to recognize when they should be thinking more thoughtfully about privacy. But it's as both mentioned, I think this kind of course has a lot of value for a lot of people outside that like intended audience. And so one more that I would like to add is Wenrong mentioned we had in the most recent offering student from Harvard Business School, a student from the Kennedy School of Government. And so these are people who likely are going to be going more into decision maker type roles, either in companies or in public policy. And so then they are coming out also with a sort of understanding of how to think scientific, kind of what are the issues and the kind of technological possibilities around data privacy much better than they otherwise would have had.
Great. On the like a pedagogical and the teaching side, how is the experience different teaching a course specifically focused on doing sort of applied DP as opposed to embedding a like smaller applied component into a theory course?
Guess we can go in this direction. So I think one thing that Wenrong mentioned is a little bit of inversion of like what is the in our course what's the priority. Like the end goal for us isn't teaching the theory. It is not building up a huge toolkit of methods. But one, it's understanding what are the problems that are trying to be solved. And so this kind of use case, kind of every topic starting with or being accompanied by some in-depth discussion of case studies, of real deployments, and what were the debates that happened, what were the difficult choices and trade-offs that had to be made, what was the pushback, came along with each of these. So kind of elevating the problems that are being tackled and the trade-offs and the challenges, I think is something that if I were just adding an implementation component to a theory course, probably wouldn't happen.
So I've never taught just a theory course, so maybe I'm not qualified to answer, but I do feel like the way I have always approached this is that I spend, probably like at least 10-15% of the time on motivation, which is just another way of saying what Salil said, right? I tend to start with like, why do we care about this? And I show headlines and like, what's the bad thing that happened and why did it happen? Or what's the story behind the controversy behind the thing? And then start to talk about what should they have thought about or what solutions can we consider for this. And so I'm definitely not starting from the toolbox. I'm starting from like, what's the bad thing that can happen?
Yeah, and I guess we came from sort of the opposite direction, which is we started with a theory course and then we added an applied course onto it. And that sort of modular course design was partially like an intentional experiment. We thought maybe it would be cool if we could have the option of people doing theory or doing both. But it was not doing both or doing applied. It was doing theory or doing both. So we're coming from a slightly different angle. I think part of the reason we did it this way, though, was sort of practical in the sense that the way we ended up going about doing the applied course is pretty resource intensive. And I would like my theory course to be able to scale sort of arbitrarily large. And I don't really quite know how to scale the way we're doing the applied course. So actually, I'm curious to hand it back and hear about how you guys scale it. If I get to ask a question as part of my answer, I'd love to hear that.
Should I go first?
Yeah, go ahead.
Okay.
Go ahead.
So it depends on what you mean by scale. So I can say a little bit about this because I've had to, my course is not huge, but I have not had a huge amount of resources to do it with. So I typically have like 70 students in my course. And the thing that has been really helpful has been to make absolutely everything a notebook and to give lots of example notebooks for everything. And so when a student like has something that's not working, they typically have like an error message to go with it. And this has meant that it's possible to, in office hours or in labs, for example, get a long way with a small amount of time, right? One of the other things that has been really helpful there has been to give students lots of reference material that is kind of built into the structure that they can't avoid. And so, for example, when I first started teaching this course, everybody would bring their laptops to class and they would sometimes take notes and sometimes just like go on Facebook or something. And so what I've started doing, and this is not just in my privacy course, but I do this in all my courses, is I have like these in-class exercise notebooks that are basically just like a place for students to take notes, but they also have to turn it in. And so like they're going to bring their laptops anyway. If I force them to do something on their laptops that's going to help them, then they'll have that as reference material when they go to do the homework. And so that's been a thing that I've been really surprised at how much positive feedback I've gotten from students on, because they initially are like, oh, it's an extra thing I have to turn in. But by the end of the course, they're like, this was the thing that really got me through the homeworks. And I think I would have a lot of trouble teaching a course of that size if they didn't have that reference material built in. So that, I mean, I use that in my compilers course too. So it's not just a privacy thing, but it's a thing that I think has been really helpful in scaling things up.
Yeah, I'm afraid we haven't really had to scale a huge amount. The first offering was 20 students. Second offering was 40 students. And lucky to be in a place where Harvard's pretty generous in its teaching staff to student ratio, especially if you're doing any sort of active learning type things in the class. They give you an even better ratio on TAs to students. And then we also, as you probably saw from the teaching staff, are also kind of leveraging the OpenDP team in the offering of this course. And I mean, that's sort of a win-win. We can justify kind of extra time there because we're learning about how to, kind of do things better in OpenDP. And, the students gave us a huge amount of feedback on the OpenDP homework, which took them forever. But then a final thing that I think also helped with the particular audience we were targeting was that we made since it was we were targeting this data science master's, we made the data science course a prerequisite. And so if I was teaching a course of theory students where we were adding an implementation component, we couldn't assume nearly that much comfort with, the implementation and experimentation and programming sense. So not all our students had that prerequisite, but we kind of designed the course under that assumption. And since most of the students had that, we didn't have to do as much handholding as we might have with a different audience.
So I have lots more questions, but I want to leave some space for the audience. Anybody have any questions they want to ask our panelists? Ludus.
Well, I really thought that like the students exploring and learning through exploration was like a really positive thing. I was wondering what parts of the course encourage that the most, or why you think that happened, I guess, more so in the applied course than the theory course.
You got the microphone.
Well, so again, maybe I'm the least qualified to answer this because I've only taught it applied, but I think just being able to see the output of something, like you type a thing and you run it and you see the output, and especially if you can see a graph, not just, although I've seen this happen just with like numbers, right? If you're like, I'm going to run the Gaussian mechanism like 25 times and just see the numbers changing, people feel like they have a better intuition if they can like try it a bunch of times and just see what happens. Or like, I change the epsilon, I run it again, and immediately I see the change in what the output looks like. I feel like a lot of my students don't have a great intuition for probabilities. And so they don't know the theory very well, or like have a great intuition for it in general. And just the ability to like run something a bunch of times and just count how many times certain things happen is just so much easier for them to understand than something, theory based about probability.
So I think maybe another thing that was going on for us is that it's somehow easier and faster to get to the boundaries of what we understand in an applied setting. It takes, sort of a semester for students in the theory course to get to the point where they could potentially ask and answer a question that nobody has asked and answered before. But in the applied course, they can kind of do it in the second week. They can just have a creative thought and, go experiment with something, and they can get there faster. And somehow it's much more accessible, this asking questions thing, in this place where, like you said, you can just type something in and run something and get a plot. And so I feel like they feel much more empowered somehow to explore and ask and try something different. But but maybe that means we're not teaching the theory right. But it just takes time to get there in theory. It takes time to get to the sort of the boundaries.
I'd like to just piggyback on what Katrina was just talking about, and specifically, makes me think want to comment on. I think one of the things that we found most exciting in the course was the project component of the course. And in the first offering, we had this plan, which was my mental model for how projects work from theory courses. Was all right. What we need to do is give them basically a list of potential projects to choose from, or at least papers. Like these are papers. Pick a paper and do a project related to that. And preparing the course for the first time, we were just so kind of overwhelmed with that. We never got around to making such a list. We made a list of types of, like, you could do a project of this type, an experimental project. You could try to bring some of the methods to some new application and data set. You could, do something trying to find vulnerabilities using some of the attack methods we learned in class. We had a list of about a dozen things you can find on our GitHub, and the students totally flourished with this very open-ended, kind of range of projects, and they came up with things that they really were able to, and I think differential privacy is particularly great for this, connected to their own interests in some way. So, there were students who were like, oh, I want to, do differential privacy for natural language processing. I want to do it on, social network analysis. And they kind of, find some of the papers in the literature, or how does DP interact with algorithmic fairness? Or then we had someone who had done an internship with some survey methodology, worked at some survey methodology company before the master's program. I want to see how using differentially private numbers and then using the result of like a census with those, using those as survey weights impacts the quality of, downstream surveys. Student who had more of a PL background. I'm going to try to, do formal verification of the components of ectalo in lean or cock or whatever, it was fantastic to see. And then actually I took that same approach to next time we taught a theory course on spectral graph theory and said, okay, I'm not going to give you a list of papers. And again, actually it worked really well there too. So it's not necessarily unique to applied DP, but I do think differential privacy is particularly good for people finding a way to connect their own interests.
More questions from the audience. Adam.
A couple of questions. So one question is, if I'd love to get find out what ways you went about teaching or giving a hands-on experience with like breaking stuff, attacks and finding problems and this stuff. Because I imagine that's very motivating. Certainly I've seen that with my students, and I'd love to hear your thoughts on that component to the class to the extent it exists.
Just real quickly, I'll be very quick on it. I mean, we start the course with attacks, as kind of to motivate the need for a principled approach, and including them having homework assignments where they're implementing the attacks, as well as reading about the Census Bureau's reconstruction attack and the attack on AirCloak, as well as some of the re-identification attacks, and students really enjoyed that. Actually, one thing that happened in the first offering that we kind of managed to push back on in the second one was too many students wanted to do their projects related to that. And we really wanted more students to like, okay, pick up on the, actually doing positive things to not just breaking things.
So I'm still trying to figure this out. I'm still trying to figure out how to teach attacks. So one thing that I do try to teach is how to debug something. And I have two ways of doing this that I've been kind of working towards. One is just like techniques for how to run the thing to see that it passes a sanity check, like make the epsilon really big and make the epsilon really small, and like make sure that things get worse and better, right? And like that, like oftentimes students will implement something and think, oh yeah, I've got it right. And then they'll try just that and realize, no, this is totally wrong, right? the other thing that I've been trying to do is checklists, because I have noticed that, students will, for example, do everything right except like forget they need to worry about sensitivity in one spot, or, something like this, right? And so as they're writing something, but also as they are trying to explain why does it satisfy differential privacy, I feel like it's a lot easier for them to do it if they have kind of a checklist of, here are the things I need to worry about in my argument that it satisfies differential privacy. And it's not like, it's kind of getting you halfway to the argument you would make in a proof, but I feel like it's less intimidating for the students to like be filling out items on a checklist to say, here's the sensitivity, here's why it's that. Here's all the places I call the mechanism and the epsilons add up. Here's like, I don't release anything that's not noisy. So all the points on my checklist are satisfied. So I don't think I have the full answer, but that's what I've done so far.
I think you're really right that attacks are really great motivation and very fun and exciting. And I can see why your students got drawn into doing projects on them. So I actually didn't have a lot on attacks in my theory course, but once we started doing the applied course, we realized that one of the things we wanted to do was to have the students build up a library of attacks that they had implemented themselves, so that then they could go and apply those on actually differentially private or potentially not differentially private algorithms and see what happened. So we ended up changing the theory course because we wanted it to line up. So there's more emphasis on attacks now in the theory course than there was before. And we structured the theory course, not coincidentally, similarly to Salil's course, sort of starting out with attacks, building up that vocabulary. But then the students literally had a library of attacks that they could go apply later on in the semester. And we had thought originally that maybe we would work up to some sort of competition at the end of the semester where students would be submitting, differentially private algorithms, and other students would be submitting attacks, and they would all be duking it out. We never got to that, in part because we built such a collaborative environment that I kind of didn't want to break that with a sort of beat 'em up kind of a competition at the end of the semester. But maybe there's a way to not destroy the sense of collaboration and still have a really fun competition at the end, because it kind of heads that way really naturally. Like, you got both sides and everybody's trying to get better and better and better. And the students did really like the assignment where we said, make this as good as you can. Not, like, here's what you have to do, but find creative things you can do to improve this algorithm. You have to get it at least as good as this benchmark, but see what you can do. They really like that kind of an open challenge, which is like one step towards this like competition kind of a thing.
Okay, so I will ask one last fast question, which is sort of, what is something that you like really learned in the process of these courses, whether it's something you maybe learned the hard way about teaching them that you did like, differently on the second time and the first time, or some kind of like an aha moment you want to share, all that insight for the room.
So I will say that, I didn't bear a lot of the pain either of the teaching or of the being the first guinea pigs of the students, but it was a lot of work the first time around, on both sides. And we were really fortunate that we had really dedicated people on both sides, both teaching and these students who suffered through like working really, really hard for a semester when I kind of told them it was going to be an easy course. But somehow it was just so much fun, I think, on both sides. Maybe you disagree. It was so much fun on both sides that like people were willing to do it, but we underestimated the amount of time that everything on both sides would take by like an enormous factor.
Yeah, so I think this is going to sound very obvious in some ways, but for me, the biggest takeaway has been, and it's a takeaway, not an aha so much, is that doing the thing really does give you a better intuition for it. And so I wish I could say a different thing now, because I feel like we've been saying this over and over again, but I feel like it really is true. And like, that should be the biggest takeaway. I've been really just so amazed at how well the students have been able to get the stuff by doing it. And like, the more doing I put into the materials, the better they seem to get it. So I feel like that has to be my takeaway.
Right. So yeah, I also feel like I said some of the kind of things I would classify as that aha in the earlier conversation, like the thing with the projects. I'd say one thing that was also a little we didn't quite anticipate how hard it would be is we really wanted to put out there polished materials that others could make use of, and we had this we have most of our things up there on this GitHub, but we wanted to also have videos of the lectures. But being privacy people, and since we were running class in a discussion-oriented way, we didn't want to make videos that included the students at all in the classroom in any public materials, and it seemed like a lot of additional work. And so that kind of just reinforces, I think, and putting my kind of OpenDP hat back on, the need for us as a community to really be sharing materials, because also in each offering, of course, the landscape is changing so quickly, the tooling that's out there, and you want to be able to update these courses. And I think we can do it most effectively by sharing. And so the educational materials repository that's got links to a bunch of things that Joe and Adam Gross have helped set up is, I think, a great start. And so I encourage everyone to try to contribute to that. And hopefully we can make offering these kinds of courses easier for everyone going forward.
Amazing. And let's thank our panelists again.